Okay, so welcome to part 2 of lecture 10 for privacy in machine learning and statistics. In this part, we'll talk about how to prove the strong composition theorem that we discussed in the first part. Remember, we ended with the idea that for differentially private algorithms, the information loss random variable, it's with high probability, it's between minus epsilon and epsilon, but its sort of average value tends to be quite a bit smaller. And now we're going to try and understand why that is. Okay, so the first thing we're going to do is we're going to have a reduction of sorts to a specific epsilon delta differentially private algorithm called Leaky, which I'll call Leaky randomized response. So this is a mechanism with only a few possible outputs, and which is somehow the canonical epsilon delta differentially private mechanism, at least once you fix two neighboring data sets that are of interest. And then we'll then show how we can show strong composition for this specific algorithm. Show strong composition for Leaky randomized response. Okay, so we're going to recall some notation to talk about Leaky randomized response. It helps to recall some notation that we've used before. So given two random variables that are defined on the same space, defined on x and y, defined on the same set, same base set with the same set of events. We'll write that, we'll write that x is indistinguishable up to parameters epsilon and delta from y, or rather it's really about the distribution. So the distribution of x is indistinguishable from the distribution of y. If and only if the for all events E in the space Y, so these are all legitimate events, we have that the probability that X lies in E is at most e to the epsilon times the probability that Y lies in E plus delta, and the probability that Y lies in E is at most e to the epsilon times the probability that X lies in E. So so this is just shorthand for the condition we want. The condition we want on the output distributions on neighboring data sets. So this condition is what we require for a of little x and a of little x prime when x and x prime are neighbors. Okay, so this is just a shorthand that we'll find useful. Okay, and what we'd like to do is understand to what extent can we kind of characterize the pairs of random variables that satisfy this relationship? Like, what does it really mean that two random variables are close in this way, that the probability of every event differs by a multiplicative factor of e to the epsilon and an additive factor of delta? And so to get our hands on that, it's helpful to try and think about what is the simplest type of random variable that exhibits these this relationship and can really get us like any relationship between epsilon and delta we want. Okay, what is this sort of simplest? That's not really well defined, but the simplest pair of random variables that satisfy this relationship. This sort of epsilon delta indistinguishability. And so in order to get our hands on this, we'll consider a pair of random variables that take only 4 possible values. In fact, each one takes only 3 possible values. And there are sort of, for these random variables, there are two types of outcomes. So there are some small probability outcomes. So small probability here means probably at most delta, that are very different for the two random variables. And with large probability, the large probability outcomes, they're only a little bit different. They differ only by the multiplicative, by this like e to the epsilon multiplicative factor. Okay, so specifically consider two random variables u and v, that take values on, so they're distributed in the set 0 and 1. And then, so the set of values they can take are 0 and 1, and then two other special values. One, which I'm just going to call it like the string IMU, which is just, it's a special value that only you can take. So if you see that value, you know that this thing was generated according to you. And another value, which I'll call IMV, and when you see that, you know it was generated according to V. Okay, so these are the four elements we'll get, and here are the distributions, so we can just sort of write them down. So let's see. Okay, so here's the probability distribution for U, and here's the probability distribution for V. And here are the four elements of the domain. Okay, and the special value IMU, that occurs with probability delta under U, but 0 under V. And the special value that says, hello, I'm V, that one appears under probability 0 under V and delta, 0 under U and delta under V. And then the remaining values, so they add up to only 1 minus delta. Yeah. And they are like, they basically behave like randomized response values. So they have the property that 0 is slightly more likely under U and slightly less likely under 1 is slightly less likely under U, and then 0 is slightly less likely under V, and 1 is slightly more likely under V. Okay, so if we were sort of to plot, you know, there are these sort of four possible outcomes. There's like IMU and 0 and 1 and IMV. Okay, and the distribution of U is sort of looks like this. It's slightly higher on 0 than on 1, and then it has like a little mass delta, little knob of probability mass on IMU, and then it's sort of the symmetric thing for V. So V looks like this. Its distribution is slightly more on 1 than on 0, and then it's like 0 here. This one has mass, U has mass 0 on V. Okay, so here the red is U and the green is V, is the mass of V. Probability mass under V. Okay, so these are the two random variables we're going to consider. And so notice that they satisfy the relationship we want, right? So there's this, if I consider any event under PU, its probability can be multiplied by at most e to the epsilon, and it can pick up a little bit of an extra delta factor And same thing, vice versa for P sub V. And so like that relationship will be tightly exhibited by U and V. But these two random variables are special in as much as any pair of random variables that are epsilon delta indistinguishable, they can be simulated by the post-processing of the pair U and V. So let me explain what I mean by that. So we'll call this the simulation lemma. Okay, so it's, I think, lemma 3.1 in the notes. And it says the following, that if X and Y are in epsilon delta indistinguishable for, so this is for every epsilon and delta greater than 0, and for every pair for every X and Y random variables which satisfy this relationship, then there exists a randomized map F such that if I run F on an input distributed according to U, it has the same distribution as X. But if I run F on an input distributed according to V, it has the same distribution as Y. Okay, so this notation here is I'm going to use to mean same distribution. Okay. So this lemma is going to be super useful for us because basically what it's going to tell us is that if we can argue that U and some property holds for U and V, and that property is closed under post-processing, then in fact it holds for every pair of random variables X and Y that are indistinguishable in this way. So just pictorially, what this means is I can find a box F, an algorithm F. If I run it on a sample from U, I get a sample from X. If I run it on a sample from V, I get a sample from Y. All right, so why is this true? Well, I'm not actually going to prove this to you. I'm going to leave the exact proof as an exercise for you guys to do in class, but I'm going to do a fair bit of it and try and give you enough structure to get started and finish up in your discussions. Okay, so so here's the way to think about what's going on in this proof, or here's a way, I suppose, to think about what's going on. So we're going to start with some distribution, some random variables X and Y. So they have some distribution. So let's say this is the distribution of X, right? And then there's some other, there's Y that has its own distribution. Okay. And what we're going to do is we're going to look at the function that's given by taking the probabilities under X and multiplying by e to the epsilon. So I should be clear that here the values we're plotting are probabilities of different elements in the domain. So here what's here is like the domain of X and Y, the domain where the set of values that X and Y take, and which we'll, for simplicity, think of as just the real numbers. All right, so let's let's look at the function e of that is like the probabilities under X multiplied by e to the epsilon. And similarly, we can look at probabilities under Y multiplied by e to the epsilon. Now, what can we say about these sets? So what we can say is that, like, what I know is that if I add up the black values, the values of P of X, I get 1, right? So the area under the curve of the P of X curve is 1. And same thing for P of Y. Same for the probability for Y. Okay, so what I'm going to think of, so I want to think of areas as probabilities in this picture. And I'm going to look at, so the area under the black curve is 1, the area under the red curve is 1. What I'm interested in is the area that's between, here, let me choose a different value, a different color. The area that's between, let's call this set A or B, well, we'll call it B. So this is the area that's between the curve for P of Y and the curve for P of X. Okay, and then we'll also consider this set here, which is the area between, sorry, so B is the area between e to the epsilon px and P of Y. So it's like the part of the probability distribution of P of Y that is not bounded above by e to the epsilon times P of X. And similarly, A is the part of the distribution under X that is not bounded above by e to the epsilon P of Y. Okay, so the kind of way to get started to understand what's going on is first to check for yourselves that the areas of these of A and B, they're at most 1. At most delta. Okay. And now, once we've got that in hand, we can sort of ask, well, what are we going to, remember, we want to try and design this function f. So we're going to consider some particular output, little y. And we're going to ask, what is the probability of, so we want, like, y to have the feature that under u, when this post-processing function f is handed a sample from u, it should be that the probability of little y, sorry, y is probably confusing symbol here. Let's use z. Okay, so what do we want? We want to assign, so for each z in the domain, we want to assign probabilities that f will produce z under each of the possible inputs to f. Okay, so of which there are 4, right? So we want the probability that f of 1 equals z, f of 0 equals z, f of I'm u equals z, and the probability that f of I am v equals z. Okay, so for each z, we need to figure out these 4 probabilities. And they're going to depend on the, they're going to depend on px and py. Let me slide this over so I have more space. Okay, so what I'm going to do is, I'm not going to fill in all of these, but let's look at the probability that I should generate this element z under IMV. So this is the, I'll fill in one of these just for you. So this is the, what I want is to sort of generate, like, get my hands on, like, this part of the probability, because the input IMV, that's going to correspond to area B in the picture, and the input IMU, that's going to correspond to the picture, the area A picture. So for example, the probability I'll assign to element z is the maximum of 0 and py of z minus e to the epsilon times px of z. Okay, so that's the length of this like black bar. So notice that's for everywhere where the red curve comes below the dashed black curve, that's 0. And for everywhere where the red curve is above the dashed black curve, that thing is positive. Okay, and so my question for you guys is like, well, what's, what are the other 3 probabilities one should see here? Okay. And so I won't say more than that, other than the fact that if you set up these probabilities properly, then you'll get the thing you want, that the distribution of f of u will be the distribution of x, and the distribution of f of y, of f of v will be the distribution of y. Okay, so this is our simulation lemma. The question is, how do we use it? Like, why is this lemma useful for proving composition? Well, to see why, let's fix 2 neighboring data sets, x and y. Sorry, x and x prime. And a partial transcript, a partial output, y1, y2, up to some point in the composition, let's say yj minus 1. And now what we can do is we can look at, these 2 distributions, the distribution of aj of x, where we've selected aj using y1 through j minus 1, versus the distribution of aj on x prime, where we've chosen aj using the same same sequence of initial outputs. So what we know is that these things are close by virtue of the fact that a sub j is differentially private for every setting of the y's. So we know this is true. So by our simulation lemma, there exists some map f of, we'll call it f sub y1 through yj, yj minus 1, such that this map, so when applied to u, it gets the same distribution as a of x, aj of x, and when applied to v, gets the same distribution as a of x prime, aj of x prime. So basically, what this means is sort of we can simulate the next output once we know, if we know x and x prime and y, the previous outputs. So we can pull the simulation off given a sample which is either from u if we're supposed to generate f of x, or v if we're supposed to generate a of x, or v if we're supposed to generate a of x prime. So how can we use this? Well, what it means is that we can write one big we can write the output of A on X and the composed algorithm A on X, or versus the composed algorithm A on X prime, as the post-processing of a sequence of IID random variables drawn according to U and V, or V. So what do I mean by that? So there exists a map F star, a randomized map F star, such that the following holds. If I run F star on a sequence of k IID samples from U, then I get something with the same distribution as the composed algorithm on input X. But if I run the same map F star on k IID samples from V, then I get the same distribution I would have gotten had I run A on the input X prime. Okay, so here U1 through UK are all independent and identically distributed according to the distribution on U, and V1 through VK are all distributed according to the distribution on V. Okay, so just to recall, here are the two distributions up here again. Right up here. So so U is the one that, like, U and V are basically, with probably delta, you get a special signal that tells you exactly whether or not you're dealing with U or with V. And with probability 1 minus delta, you get like a randomized response bit that gives you a slight signal, but not high confidence. Okay. So this follows more or less directly from what we were just saying. Sorry, let me align that properly. So so let's define F star. Okay. So F star gets an input which consists of k symbols from this 4-symbol alphabet, which I'll just abbreviate like this. Okay. F star does the following. For j equals 1 to k. So the first thing it'll do is it'll sample an output. It'll sort of, at each stage, it'll sample an output yj by running this randomized map F on zj, and which randomized map F, by running the randomized map corresponding to the prefix y sub j minus 1 on input zj. Okay, and that's it. We don't need to number steps. Then it just returns y1 through yj when it's done, yk when it's done. Okay, so this is our procedure. And we can prove that it's correct by induction. So like by induction, each yj is distributed in the correct way. Okay. Each yj is distributed according to whichever thing it should be distributed to. So according to like a of x, y1 through yj minus 1, if zj came from u, and it's distributed according to a of x prime and y1 through yj minus 1, if zj is distributed according to v. Okay, so that I claim we're done. So what have we shown? We've shown that the algorithm A is the composed algorithm A can be, once we fix data sets x and x prime, the composed algorithm A can be written as the post-processing of the pair of either a tuple. Sorry, let me try that again. The composed algorithm A can be written as the post-processing of either a tuple of values distributed IID according to U, or a tuple of values distributed IID according to V. Okay. And so what that means is that, so this is the important consequence of all this. If I can prove that this tuple U1 through UK is epsilon tilde delta close to the tuple V1 through VK, then by post-processing, by closure under post-processing, we know that A of x is epsilon tilde delta close, delta tilde close to A of x prime. And so at that point, we're done, right? So then we're done. Right, and hooray, then we can go home. So this whole simulation argument has been to kind of give a reduction from the general case of composition, which I promise you, if you try to prove directly is a bear, to something that's actually pretty simple to think about, which is just like, how close are these two distributions? One is IID, KID copies of U, and the other is KIID copies of V. So our last little lemma, let's call it 3.3, is that KID copies of U are epsilon delta tilde indistinguishable from KIID copies of V for epsilon and delta as in the theorem. Epsilon and delta tilde as in the theorem. So just so just as a reminder, since it's been a while, here delta tilde, we wanted it to be K times delta plus delta prime. And epsilon tilde, we wanted that to be epsilon times square root of 2k ln of 1 over delta prime, plus this extra term that we said doesn't usually change things much. Okay. So we're down to this, and once we prove this lemma, we're all done. We've proved the strong composition theorem. All right, so let's just do that. So we're gonna set up some bad sets that have probability delta tilde. And under, once we're outside of that bad set, then we're going to argue that the information loss random variable is not too high. So let's look at that. Let's look at the log of. Okay, let's call it this. So given a particular value, z1 through zk, that's again so the z's take these four, can take each of these four values. So given a vector, let's look at, so we can call this thing z, I of z. So this is the log of the probability that we get z under when the random variables are distributed according to u over the probability of the same thing happening under v. And again, we can write this as a sum. So now we just want to think a little more about this specific summation. And we want to understand when is this sum big and when is it small? So we're going to look at two bad events. Two bad events. So bad one is going to be the event that one of these z values just gives up the game and tells us has the value either IMU or IMV. So bad one is the set of z's where some entry in z is either I'm U or hey, I'm V. Okay, so and the complement of bad one is when all of the inputs are either 0 or 1. Okay, so notice if bad one occurs, then this information ratio is either plus infinity or minus infinity, but it's definitely not a nicely bounded random variable. On the other hand, I know that if z is distributed according to k copies of u, then the probability that it lies in bad one is exactly k times delta. Okay, sorry, it's not exact. It's at most k times delta by a union bound, because there are k bad things that can happen. Each one can happen with probability at most delta by the union bound. Okay, my second event, the second event is going to happen is going to be a subset of the complement of bad one. So if bad one does not happen, right, then the zi's are actually in 0 or just either 0 or 1. And then we are going to look at the probability. So bad 2 is just going to be the probability that So that's the set of z's, the probability that the sum is too big. The set of z's where that are not in bad one, such that this information ratio exceeds epsilon tilde. Okay, and so the remainder of the work is to argue that bad 2 doesn't happen with high probability, and basically we've picked epsilon tilde to make that happen, and I'll just sort of explain why that is. All right. Sorry, so let me try and keep the lemma in sight as long as I can. So what we want is to so let's look at what happens when z is when the z's are just 0 or 1. So if z is really in 0, 1 to the k, so if that is if bad 1 doesn't happen, then the log of the probability that uj is equal to the probability of zj under u and the probability of vj under u, this ratio is either e to the epsilon or e to the minus epsilon. And so the log of that is either plus epsilon or minus epsilon. And so it's very similar to the randomized response case we had before. So actually what we get is like epsilon times minus 1 to the zj. So that's either 1 or minus 1, depending on whether zj is 0 or 1. All right, and so in that case, we get that this sum we care about is epsilon times the sum from j equals 1 to k of minus 1 to the zj. All right, so let's look at how these terms are distributed under U. So conditioned on U lying in 0, 1, we get that it has probability e to the epsilon over e to the epsilon plus 1 of being 0, and probability e to the epsilon over e to the epsilon plus 1 of 1 over e to the epsilon plus 1 being 1. Okay, and that's just because that you can just see that from the way we define the probabilities. Okay, so what can we conclude from that? That I of z under this when we're in the world where bad 1 does not happen, so conditioned on not bad 1 not happening, I of z is a sum of IID random variables in each term in the sum is between minus epsilon and epsilon, and their expectation is epsilon times e to the epsilon minus 1 over e to the epsilon plus 1. That was the calculation we did for randomized response. And so by a Chernoff bound, we get the following, that so let's just write it out fully. So that under z1 to zk drawn from IID from U, the distribution of U. The probability that I of Z exceeds, so we're going to look at the probability that it exceeds something given that, bad one did not happen. So given the complement of bad one. And we're going to look at the probability that it exceeds its expectation. So its expectation is K times epsilon times e to the epsilon minus 1 over e to the epsilon plus 1. Plus t times epsilon square root of K. And the epsilon here comes from the second epsilon. This one comes from the fact that the random variable takes values in an interval between minus epsilon and epsilon. Okay, so the probability that it exceeds, so this is, again, just to be clear, this is the expectation. Plus t times the range times square root of K is in fact bounded above by e to the minus t squared over 2. And so now we just plug in if we plug in t equals square root of 2 ln 1 over delta, I think we get exactly what we need. So what we get is that the probability of like the second kind of bad event, bad 2, given that we haven't had the first kind of bad event, bad 1, is at most delta prime. Okay, where bad 2 is exactly like this. This thing happening. Okay, so I claim we're pretty much done. So what we've shown is that the probability that this random variable that we're concerned with, when Z is like is distributed according to U, the probability that this thing exceeds epsilon tilde is at most delta prime. And the proof we also have to prove the same thing with U and V reversed. So the proof with U and V reversed is completely identical, everything's symmetric. So the proof where we swap U and V is the same. It's just a symmetric case, so I won't bother to write it out. So we're done. Okay. So so what have we shown? Let's just kind of back out, one step at a time. We've shown Lemma 3.3, which says that the sequence of UKs and VKs is epsilon delta close in the sense we want. There's no any particular event, its probability gets inflated by at most e to the epsilon tilde and increased by at most additive, like plus delta tilde. So that's Lemma 3.3. Popping up a level, Lemma 3.3 allowed us to show that A, the composed algorithm, is epsilon delta indistinguishable. Okay, this statement here. And that's because we showed this statement holds for any neighboring pair of data sets. Okay, so we did this by, we fixed a pair of neighboring data sets. We found a post-processing of the vector of u's and the vector of v's that yield the two distributions we care about. And that allows us to understand how close they are. Finally, what does this all get us? So let's just sort of zoom way back out to the top. It's allowed us to show the theorem we started out with that we wanted to show, which was that if we look at the adaptive composition of K algorithms, each of which is epsilon delta differentially private, then we get an algorithm whose final privacy guarantee is about epsilon squared of K, and whose final like delta guarantee is about delta times K. Okay, so, and that is enough for in particular to, like, you know, one application of that was to answer K adaptively selected counting queries with relatively little noise. And then we'll see more applications next time when we talk about gradient descent. One last thing I want to mention is that this same proof technique we have, this idea of like decomposing things in terms of the U's and V's, that's a very general proof technique for understanding both composition and well, for understanding, yeah, I guess mostly composition. It turns out to be useful for other things. But in particular, you know, there's a recipe there for getting bounds. For example, if the epsilons of the various algorithms we run are not all the same, then we can still get a bound. We can still get, like, so the theorem as I wrote it doesn't apply anymore because the theorem requires them all to be the same. But you can sort of work through what happens in that proof and get bounds for whatever setting you need. Okay, so that, like, you know, whatever sequence of epsilons and deltas your individual little algorithm satisfy, you can find a sequence of U's and V's with appropriate parameters that sort of capture the behavior of the algorithm on two neighboring data sets, and you can just sort of analyze that to get as tight as you want, as tight as possible, a guarantee, like a privacy analysis. And it turns out that's not a trivial thing to do in general, but, like, you know, there's a general recipe for how to proceed. And so in class we'll see how to use that recipe to prove the basic composition theorem, which I just want to highlight. We haven't yet seen a proof of, right? So we've proved advanced composition, but we haven't totally proved basic composition for epsilon delta DP algorithms. But once we have this simulation lemma, that becomes pretty straightforward, and that's going to be one of our in-class exercises. So I'll see you all on Tuesday, and I hope you have a good couple of days between now and then.